In Calc 2, we studied equations of the form dv dt equals some function of t, such as dv dt equals 2t, and found families of antiderivatives, such as v of t equals t squared plus c in the example above. While we didn't call it that at the time, these are differential equations because they're equations that involve a derivative. In this course, we'll study differential equations of the form dv dt equals some function of both v and t, that are functions of both the dependent and independent variable. Since differential equations and integration are both rooted in the process of using information about the derivative to find information about the original function, integration will be involved in many of our techniques to solve differential equations. For us to be able to solve our first differential equation, we'll need to remember the substitution rule from Calc 2 that says the integral of f of v times dv dt is equal to f of v dv. This is going to be key in our first method of solving differential equations. To see where this rule plays a pivotal role, let's look at the example where we want to solve the differential equation dv dt is equal to v. Notice here that this would not be the type of differential equation that we would have seen in a Calc 2 class. What makes it different is that the equation involving the derivative of v is also a function of v itself. As I said, we're going to need to use the substitution rule. And in order to use the substitution rule, we need to write the left-hand side as some function f of v times dv dt for some function f of v. We can attain this form by multiplying both sides by 1 over v to get 1 over v times dv dt is equal to 1. Now that we have it in this form, we can use the substitution rule by integrating both sides with respect to t. So on the left, we have the integral of 1 over v times dv dt is equal to the integral of 1 dt, which simplifies to simply t plus c. Since we'll get a constant of integration on both sides, I'm going to call this t plus c1. And then using the substitution rule on the left, the integral of 1 over v times dv dt is going to be the integral of 1 over v dv. So we can rewrite that on our left-hand side. And this left-hand side integrates to the natural log of v plus some constant c, which we'll write as the ln of the absolute value of v plus c2, since it may be a different constant of integration as the one on the right-hand side. And combining the two ends of our equation, we get that the natural log of the absolute value of v plus c2 is equal to 1 plus c1. And since c1 and c2 are both constants, we can simplify this as the natural log of absolute value v is equal to t plus some constant c, where that single constant c is equal to c1 minus c2. Notice here that we no longer have a differential equation for v. Rather, we have the algebraic equation, the natural log of absolute value v is equal to t plus c. So from here, we'll only need to use some algebra to find what v is. To start the algebraic process to solve for v, we'll exponentiate both sides to undo the natural log and get e to the natural log of absolute value v is equal to e to t plus c. And the left-hand side reduces to just the absolute value of v, which is why we exponentiated. So we have the absolute value of v is equal to e to the t plus c, which we can split up as e to the c times e to the t. So we have absolute value v is equal to e to the c times e to the t. And thus v itself is either plus or minus e to the c times e to the t. And since c is constant, e to the c is constant as well, and so is plus or minus e to the c. So we can rewrite this coefficient plus or minus e to the c as some new constant k. And we can conclude that the solutions of our differential equation are all of the form v equals some constant k times e to the t. And we've just solved our first differential equation of the course.